Hello, my name is Jumel Ziu. I'll be presenting the heat exchanger versus reactor, looking at the role of dynamic temperature versus fluid velocity profile. So what we're trying to do is we're trying to explore the critical difference in temperature control and fluid dynamic between the heat exchanger and chemical reaction through the use of data science. The equipment. We will be talking about how the temperature is controlled, how the system differ, and then the performance factor. So why it's important? Because on the temperature control, it's essential in chemical engineering with different dynamic between systems, and why the system difference is crucial because when we talk about heat exchanger and chemical reactor, they operate in different principles. And then the factor that look at the performance, we'll be looking at the fluid dynamic profile, and then the temperature evolution, as well as the efficiency. So on the heat exchangers, how stable the temperature is and predictable the flow is. So on the heat exchanger rate, we observed that there was an increased velocity boost with convection, but rise with pressure drop. Efficiency and fouling, we observed that a low velocity leads to fouling and reducing the performance, which leads to uniformity and help balance the flow, which avoids hot spots and promotes a system integrity. So this is basically how it is visualized on the right hand side. So why do we worry so much on the dynamic of the temperature and changing flow in reactor? Well, because we want to look at the reaction rate, because the velocity controls the residence time and the reaction completeness. So if we don't control the velocity, or at least we don't know how to monitor that, then we can see that it can lead to basically accident and explosion. So we don't want that. And the other aspect is like the mixing and heat removal. So we observe usually like turbulence, which adds with mixing, and the laminar flow might cause hot spot. So that's why we also concerned about mixing and removal of heat, and the selectivity and yields. So the velocity enhance, like tuning, enhance the product yield. So that's why it is crucial as well. On the heat exchanger versus reactor, so we made the comparison a little bit here. So on the heat exchanger side, we want to optimize, like it optimizes, for the steady velocity and thermal uniformity. So we want to make sure like, the heat is uniform across. That way we don't have too much heat dissipation. And then on the reactor side, which requires a flexible control, to respond to the kinetic energy changes. So we have to basically, make sure that is flexible. Otherwise, for safety purposes also. So here we were able to look at the profile, the reactor temperature distribution, and we could gauge, the time as well as like the position. And then the yellow side is basically like the hardest place and the temperature in Kelvin. And then the heat exchanger mid-length temperature. So the one observed coincide basically with like the predicted uh, value of the heat prediction, which was actually a good indication that we were on the right spot. So why, what is the advantage of the tools and then the real-time monitoring? Well, it's for computational fluid dynamics, which simulate complex flow patterns and heat transfer in a 3D space. So with the help of also predictive fouling detection as well as data science, we identify early signs of efficiency loss before critical failure. So we make sure we we are proactive basically to just prevent failure, because if we don't, then accident can happen and boom, explosion. And then also we have the energy optimization. Why? Because we want to reduce the operational cost through a precise control algorithm, because energy costs money. So if we don't reduce the operational cost, then it will be costly. So, and then also for safety purposes to prevent runaway reaction through early warning system. So this on the predictive model summary, those were actually the result that we got from running the code in Python in the system. So the reactor temperature, we had a root mean square error of zero point 0.4 and R square of 0.00. The insight, that means basically early warning for runaway reaction and PID tuning. On the heat exchanger, we had a very small RMSE 0.002, and the R square was actually high, which actually predicts the fouling and ensure thermal reliability. Because the R square being 1 means, it's not really realistic to have 1. That means it's a perfect, you know, a system, which barely occurs in industry, but for simulation purposes that was actually the case. So for the pipe velocity, we observe 0.07 for RMSE, and then zero point 0.9 for this one was actually reliable, because in a piping system it's just reliable on that. So that was actually a good indication as well. So on our exploratory data analysis summary across the three systems, we observed that we had close to 400 Kelvin as the maximum reaction temperature on the upper limits for safe operation, and 1 meter per second for the maximum pipe velocity to optimize the flow rate for efficiency. And then the maximum heat exchanger temperature was 200 degrees Celsius, which was considered a critical design parameter. And also, to get more insights on the reactor temperature heat map, we observed that the hot zone was approximately 380 Kelvin, which was an indication on the yellow region, and it indicates a reactive inlet area with a rapid exothermic reaction. That means it just releases heat. And on the stable zone around 300 Kelvin, the tilt region, which shows optimal core operation condition with efficient heat removal. So as heat was being transferred basically, so that's why it basically means. And on the cool zone, less than 225 Kelvin, where the purple region suggested reactant deficient area, which requires process adjustment. So in that zone we needed adjustments. So that was basically the insight that we observed. And then here was actually the plots that actually describe the system. And on the left hand side we had a reactor temperature prediction. And as you can see, the observe on the oscillated, because we observed reaction, and then the predicted was actually the orange dotted line, and which makes sense basically because the temperature was decreasing, which was actually an indication of heat being transferred. And then on the right hand side, for the velocity trend along the pipe, we observe on the the blue line was representing the velocity observed, and then also on the dotted orange line was the predicted. So a little bit coincide, and also that means that okay, as we move away from the center, so the velocity actually, I mean, as we move away from the center, we decrease basically like the velocity. So how does data science is linked to this engineering like project? Well, one for digital twins, real time simulation and adjustment, because of data science we were able to actually uh, observe those elements, and it helped us predict the models by forecasting the temperature spike, as you could see earlier. And we were also able to visualize the tools by detecting the anomaly like quickly. And then we also run like a cluster thermal and flow behavior using the PCA, the principal component analysis, as well as the k-means clustering to reveal like three distinct operational zones across the reactor, pipe, and heat exchanger system. So this was actually what the plot was, and we had like different groups here represented by the yellow, I mean the blue, red, and green. And then on the right hand side, we had also the fluid velocity profile, which was actually an indication of how the velocity basically behaves, the fluid behave in the the piping system. So as you can see here, like we had more higher velocity at the center basically of the pipe. And also we observe the dynamic temperature in the reactor with the 3D observation as I described earlier, as well as in the heat exchanger. So why we also talk about industrial impact, predictive maintenance to anticipate, cavities, thermal instability before failure occur, cost reduction by optimizing the energy usage and extend equipment life through data-driven decision making, and also to make smart plans which enable sensor-driven feedback and automated control system for continuous improvement. So the final thought here would be basically, to combine chemical engineering fundamental with data science tools to empower industry and predict failure, efficiency, improve safety, as well as better decision making at a faster rate. That concludes our presentation for today. Thank you very much and have a wonderful day.